Okay, we're going to get started. Good afternoon, good morning, and good evening to everybody tuning in from across the world. Welcome to the Moberg Analytics monthly neurocritical care webinar series, where we go through case studies in neurocritical care and AI, and talk about all kinds of cutting-edge research that's being done to advance the field. This is Justin Moore speaking. I'm a data scientist and machine learning engineer on the Moberg Analytics development team, and I have the honor of hosting our webinar today. This will be our 14th episode out of many more, and I can't wait to get started. Before we do, part of the reason we do this webinar series is because we know that understanding and treating brain injury is a monumental task. Our goal as a company is to help you in that mission by providing tools and products, but also this webinar series where we bring talented minds together and showcase the amazing work that's being done all across the world to push the boundaries and change the way that we understand brain injury. Our episodes showcase the work of researchers who often include unique case studies and examples that demonstrate their work, and sometimes they also include tutorials on how you can use the methods and models for yourself. We always want to improve these talks, so afterwards, leave us some feedback. We'd love to hear what topics you want to learn about, or if you have somebody you'd really like to hear speak about their work in neurocritical care. It could be you. I know a lot of you tuning in either have work that you'd like to share or friends that are working on some really cool stuff, and we'd love to hear from you. So please leave us a response or some feedback by heading to the shortened link bit.ly/Moberg webinar feedback, or by sending our CTO Craig an email at craig@moberganalytics.com. Just a quick recap. This is our 14th episode, and here are all the previous episodes if you're watching this on our website or YouTube and feel like jumping to a specific topic. And if you're here live and you feel like catching up, you can check those out after this. If you have any questions you'd like to ask the speakers during the webinar, please leave them in the Q&A section by opening up the Zoom menu at the bottom of the screen. I'll be able to see your questions and then I can forward them. Today's speakers are doing some fascinating work on an automated technique to detect cortical spreading depolarizations using scalp electroencephalography. Dr. Alireza Chamanzar has a background in electrical and computer engineering with multiple degrees from Carnegie Mellon University. While getting his PhD at Carnegie Mellon, he developed WAVEFRONT, a non-invasive automated method for detecting cortical spreading depolarizations. He also has developed several other patented neuro-diagnostic algorithms, including SilenceMap and CSD-STGAT. Dr. Chamanzar recently started working as an assistant professor at the University of Pittsburgh and is continuing to apply AI to healthcare at CPACE, the Computational Pathology and AI Center of Excellence. John is also at Precision Neuroscopics and has a background in biomedical engineering with a focus on neural engineering. He has degrees from both the University of Florida and Carnegie Mellon University. While getting his master's degree at Carnegie Mellon, he focused on neural signal processing and also interned for several biotech startup companies where his passion for bringing new healthcare technologies to patients grew. He's currently working as a software engineer at Precision Neuroscopics and leading the efforts to develop WaveFront into an intuitive and practical tool for the researchers and clinicians. So guys, welcome.
Thank you so much, Justin, for the nice introduction. We're glad to be here. We are excited to have this webinar together.
Thank you for having us.
Can you say that again, John? Just want to make sure your mic's working.
Oh, I just said thank you for having us. All good?
Perfect.
Sweet.
Yeah, I don't want to give too much away, but I've heard your wavefront model is incredibly good, and you're using a method that's novel and less invasive. Is that correct?
Yeah, that's exactly the plan. Non-invasive diagnostic monitoring methods for a wide variety of neurological disorders. Today, we're going to talk about traumatic brain injury, worsening brain damage. Yeah.
Fantastic. All right, I'll let you guys take it away then.
Thank you so much. So let me start by sharing my screen. Let me know if you can see the screen. Can you see the slide?
Yeah, looks great.
Awesome. Great. Thank you so much for the introduction and inviting us today to talk about our work. So this work that we are presenting today is a follow-up on our previous efforts on automated non-invasive SD detection based on a multi-center cohort. This is based on a great and unique collaboration with University of Cincinnati, with Dr. Jed Hardings, University of Pittsburgh, Dr. Jonathan Elmer and Lori Shutter, Mass General Hospital, Dr. Eric Rosenthal, head of Neuro ICU, and David Chong, and Charité University of Berlin with Dr. Jens de Rier and his group. And this multi-center collaboration happened over the past few years of our conversation at International Conference on the Spreading Depolarization ICSD meeting. And this talk today that I'm giving you, the first part of the talk, is actually my talk from the ICSD this year that I gave a couple of weeks ago. So with that, let's get started. Here are our disclosures. So I first briefly talk about the clinical relevance of this work, and then give you an overview of the results. Of course, challenges in non-invasive SD detection, we'll talk about that. And then we will get into details of the results and talk a little bit about the limitations and the future work. Spreading depolarization is a potentially treatable mechanism of secondary brain injury following traumatic brain injury and subarachnoid hemorrhage. Increasing number of studies explore the potential of CSDs as a therapeutic target in traumatic brain injury and subarachnoid hemorrhage. Gold standard for SD monitoring right now is invasive intracranial recording with limited spatial coverage of the brain. It's just a kind of like a strip like this, and it only covers small part of the brain. But non-invasive scalp EEG provides a global spatial coverage of the whole brain, and it enables continuous monitoring at ICUs. Large frequency of SDs or their widths indicate increased chance of worsening brain injuries. Based on this information, the clinicians can stop and inhibit CSD waves using anesthetics, vasodilators, or even neurostimulation techniques such as vagus nerve stimulation that have been shown and explored in the literature. So detection and parameter estimation of SDs can inform clinical interventions. The first part of the results that I'm presenting today is about non-invasive SD detection in a group of skull-absent patients with a 720 total as a number of SD episodes, where part of the skull is missing, as you can see in this MRI scan, and the recording happens where this bone flap is missing. So Harding et al. 2014 and Drancon et al. 2012, they both showed that EEG carries signatures of SDs in skull-absent patients. Using EEG, we could get a detection accuracy of 85% with less than 3% false alarm rate. This is exciting, but still the skull is missing, as you can see here, so it's not fully non-invasive. The second group of patients, though, in this study includes 17 traumatic brain injury and subarachnoid hemorrhage patients with around 400 total number of SDs, where the skull is in place during the simultaneous scalp and intracranial EEG recording. The reported negative results for finding SDs in EEG in skull-present patients with and without invasive evidence in the literature motivated us to look harder. Based on our recent results, we get a detection accuracy of 87% true positive rate with less than 2% false alarm in delta band EEG. So put everything together, we have in this multi-center cohort, we have 32 patients with more than 1,100 number of SDs, where we get an average accuracy of 88% with less than 4% false alarm. Now with that, let's talk about a little bit of the challenges of non-invasive SD detection and better understand the physics of the problem, and then jump into the details of the results. So non-invasive SD detection, of course, is challenging. One reason is because of the presence of sulci and gyra and the fact that EEG is less sensitive to the activities deep inside the brain. So it is hard to perform spatiotemporal inspection of the signal time traces. This is, we're talking about hours or days of continuous recording in ICUs, and visual inspection is hard, but this is potentially an easier task for an algorithm in an automated way. Another challenge is the fact that EEG inherently is noisier recording than invasive recording. Baseline power changes over time, even across electrodes, as you can see in this example here. Non-propagating depressions in low-density EEG is a challenge for us to distinguish and like reject them against like actual STs that we're interested in. Spatial blurring of the multiple layers of the head, including cerebrospinal fluid, CSF, skull, and even scalp, they all act as spatial low-pass filters that makes it even harder to pick up the signatures of narrow STs and scalp. Also, the patient types and groups that we are looking into, they have defects in their skull fractures following the primary insult to the brain and to the head, and that causes a phenomenon called bridge rhythm, which is an increase in the low frequency components of EEG, as well as air pocket accumulations underneath the part that we are recording non-invasively. They all pose challenges for non-invasive monitoring. So other than these inherent challenges related to the physics of the problem, there are challenges specific to the study and the data sets that we have used, such as the variability of data quality from different amplifiers, partial, as you can see here, versus full standard scalp coverage. The Berlin data set, they had older amplifiers and partial scalp coverage. In your patients, they had like a standard Moberg 1020 system. And also we had to deal with challenges of synchronization between EEG on scalp and electrocorticography or ECOG signal amplifiers where we get the ground truth from. Also, we had to deal with some missing electrode labels and locations on scalp. So in this work, we bring all data into a standard format using tailored data cleaning process for each cohort and data type, and enable non-invasive SD detection through the main steps of our algorithm. We use WAVEFRONT technique in this study, which was first proposed back in 2019 and then modified and applied on real human data last year that a paper came out that was based on the University of Cincinnati cohort. For the interest of time, I'm going to skip the details of the algorithm here, but if you're interested to learn more, please check out our papers on WAVEFRONT. So now let's jump into the exciting recent result that we got using WAVEFRONT. This multi-center cohort includes patients from 3 centers with different types of injuries and skull conditions, so it's a rich data set. This data set includes patients with a wide range of number of STs between 0 to 200 per patient, with around 1,100 total number of STs across 32 patients, just to give an overview of the this data set. In this study, we only focus on patients with strip electrodes and exclude patients with depth electrodes. The reason is that ST electrodes, depth electrodes have been shown to be less effective in capturing STs and less reliable to be used as ST ground truth, because the spreading depolarization is a cortical wave that travels across the cortex, and depth electrodes does not capture that traveling across the cortical surface. So we validated the performance of our WAVEFRONT on this multi-center cohort through cross-validation, closely following the steps in our 2023 paper. We trained our model on 28 patients and left 4 patients out for the validation, and repeated this process for all the possible selections of the validation set. For this multi-center cohort, we get a detection rate of 89%, a true positive rate with less than 4% false alarm, where the true positive rates and false positive rates are calculated in overlapping time windows of 2 minutes. Here is the ROC curve for the average train and average validation performance, as you can see in blue and red. And the optimal operating point in the validation ROC curve comes from a cross-validation error matrix that we defined, which provides a trade-off between the precision and recall. Harding et al. 2014 and Chamanzar et al. 2023, they both showed that delta band EEG has the best performance for non-invasive SD detection, and that's the frequency band that we went with for this multi-center cohort. We have done similar cross-validation analysis for 3 centers. 2 injury types of TBI and subarachnoid hemorrhage. We excluded the malignant hemispheric stroke patients because of a small number of patients and the lack of feasibility to do cross-validation. And also we did that for different skull conditions and all the patients altogether. So these validation results indicate that WAVEFRONT, if trained on sufficient data on each patient category, can reliably detect and track STs within each group. But the main question is that, is it really generalizable if we train on one group and test it on another group? To be able to answer this question, we obtained generalizability ROC curves where the pre-trained model from one group is applied on another group. And we did that for centers, injury types, and skull conditions. And we observed the general trends of generalizability, including strong unidirectional generalizability from skull present to skull absent, as well as from TBI to subarachnoid hemorrhage. More importantly, we see that once WAVEFRONT is trained on all patients, it works well on patients with different conditions. Now, let's take a look at the spatiotemporal illustration of propagating depression on scalp in a TBI patient on the left side and a subarachnoid hemorrhage patient on the right-hand side. These red bumps, as you can see here, are the detected power depressions on scalp. And of course, these are the ECOG recordings on the bottom. This is the top view of scalp where the blue spots that are moving around are the depressions. And as you can see here, some of the propagations are happening starting around P3, slowly moving towards P7, T7, and O1. And also on the right-hand side, we see that the propagation starts around F3 and it goes towards F7, FZ, C3, and T3. So in both examples, there is a clear spatiotemporal consistency between what we observe on scalp using WAVEFRONT technique and what's going on in the ECOG recordings, which is promising. And here is a detection in a bigger time window of 30 hours for a skull present TBI with 6 SDs. And in the middle, we can see the annotated SDs as these dashed green lines. And then on the bottom, the red bars are the output of the WAVEFRONT, the detected parts. As you can see, we detect around the correct part where we have the annotated SDs and also this small part, which may or may not be a false alarm, and that requires revisiting the annotations of ECOG, see whether there was actually a SD or not. So I conclude this part of the talk by going the limitations and the future works. So we have shown in our results that WAVEFRONT suffers from under detection of cluster SDs, which are the SDs which are too close to each other over time. So more than 3 SDs in less than 2 hours, or there's a variation of definitions of cluster SDs. It's called clustered SD. And of course, because of the inherent limitation of EEG, it's hard to pick up each of them individually. So of course, larger data set with a higher density of EEG electrodes will improve the validation performance. That's our next step. And we are also going to work based on more advanced end-to-end deep learning techniques for non-invasive SD detection, as well as parameter estimation, such as our recent CSD-STGAT spatiotemporal graph attention technique that we proposed last year, which can estimate the widths of CSD using simulated scalp EEG signals with less than 11% normalized error. So this is yet to be tested on human data, and we're excited to see how does that perform on this multi-center cohort. That's also a big next step for us. So there's a recent cool idea of single channel SD detection using EEG spectrogram by Wu, Jewel, and others. And we are very interested to try this idea by adding the frequency as a third feature dimension to the space and time that we have and see how does that improve the results. So once we have this non-invasive SD detector, there are exciting questions that we can ask, such as, can we predict patient outcome using WAVEFRONT and its SD detection on scalp? Does the location of detection, for example, left versus right hemisphere, predict the location of secondary brain injury in the brain? Do patients with higher number of detections have more fluctuation or delayed recovery? And finally, can WAVEFRONT suggest the correct interventions for these patients that warrant a retrospective study? And we are actively working on that on a cohort of patients where the outcome is present. With that, I'll stop here and hand it over to our amazing software engineer, John, to talk about our software development efforts. John, please.
Awesome. Thank you so much, Alireza, for that wonderful portion of your talk and for that great overview of the WAVEFRONT algorithm. Oh, you can go ahead and keep sharing your screen.
Oh, sure. So you want to go from here? Let me. There we go.
Cool. So yeah, we'll now shift gears a little bit from talking about the WAVEFRONT algorithm itself to talking more about some of the software development efforts surrounding WAVEFRONT. And so the primary motivation for our software development efforts is to turn WAVEFRONT into a tool for both clinicians and researchers. And so this is a brief outline of my portion of the talk. So we'll start a little bit about how we've gotten to where we're at. And the first major step of that was kind of taking WAVEFRONT and translating it from a MATLAB environment into Python. Then we'll take a look at an overview of the GUI. We'll talk about online versus offline and kind of what that means a little bit more here in a bit. Then we'll touch on some of the features of the GUI, kind of explore those in a little bit more detail. Talk about some next steps for our software development efforts. And then finally, at the end, we'll do a little demo of the GUI working in real time. Awesome. So you can go to the next slide. Awesome. So as I mentioned, the first big step in our software development efforts were taking WAVEFRONT from MATLAB into Python. And there were a couple reasons that we wanted to do this. So the first big one was MATLAB is great for those familiar with MATLAB, but it's not as suitable for software development and kind of giving it to a generalized audience for CSD detection, specifically for clinicians and that kind of side of things. Essentially, we don't want to hand clinicians a bunch of MATLAB scripts and expect them to know what to do with them. So that's a big motivation for taking it out of MATLAB and into Python. And additionally, it removes the need for a MathWorks license. So MathWorks licenses are great if you're in academia or a student, but as soon as you get out of that environment, they become a lot more expensive and it becomes a much bigger burden, especially if you need the base package and additional toolboxes, which the WAVEFRONT preprocessing pipeline and algorithm both require. So a lot of reasons to kind of get it out of MATLAB and into Python. Another big advantage Python gives us is a lot of optimization ability. So there's a wide range of signal processing libraries to pick from. So there's a handful of functions we can pull from different libraries to optimize the overall algorithm. And so when you're working in MATLAB, all your functions essentially come directly from MathWorks, and you have some flexibility into the parameters and things of those functions. But ultimately, having a wide range of options for all of our functions has given us a lot of successful results in optimization. Additionally, Python gives us the ability for some parallel processing in the form of both multi-processing techniques and multi-threading techniques. And we've had a lot of optimization success with both of those in various use cases. And then finally, what the bulk of the rest of my portion of the talk will be about is translating into Python allows us for more intuitive displaying of the wavefront results. So specifically, the GUI that I'll be presenting is built on a framework titled DearPy GUI or DearPy GUI, depending how you pronounce it. But yeah, ultimately, just the greater flexibility of displaying the results is another big motivation. So with that, you can go ahead to the next slide. Cool. Oh, and by the way, if anyone has any questions at any point, feel free to stop me and ask. So here is an overview of the GUI. So we'll dive into each of these points a little more in depth, but at a high level, we want to design the GUI to feel very familiar and comfortable for our end users. So we wanted to model it after existing EEG viewers, and essentially we want to create as little disruption to existing workflows as possible. And that's kind of the motivation behind the current design. But at the same time, we have novel insights to provide in the form of our CSD detections. So we aim to kind of balance the familiar environment with this novel insights. Additionally, one of my favorite parts about the GUI is we can view some intermediate pipeline data and not just the pure inputs and outputs. And I really like that because I feel it adds to, excuse me, the overall trustworthiness and transparency of the pipeline itself. So this is awesome, especially for clinical uses, because clinicians don't want black boxes. So I really love that the transparency that this adds. And then finally, there's two flavors, as I mentioned, offline and online. And for now, just the motivation for each. Offline is more for researchers, whereas online simulates our clinical setting and what Wavefront might look like once it finally reaches the clinic. Yeah, you can go ahead. So to quickly orient everyone with what we're looking at here, we'll go over some quick data assumptions of the GUI, and these are pulled pretty much directly from the algorithm itself. So that's kind of why it's set up this way for the moment. And so for the GUI, the first thing that you're going to want to go to is your patient ID, and this is just a dummy cohort right here. But for this example, we would go ahead and just select sample patient ID A. And go ahead, Alireza, the next slide. And that will populate this data session menu tab button with all the recording sessions for that specific patient ID. So for this specific patient, there were 3 recording sessions. Recording sessions can be anywhere from about 4 to 6 hours, or 4 hours to all the way up to about 30 hours. So these vary greatly, but these are just sort of the units of data that we have at a high level. And so that's once a user selects one of these recording sessions, this field here will populate with the entire recording session. So right now, this is August 18th, specifically with the Delta band data, but we'll jump into all that a little more. I just wanted to kind of give everyone an idea of what we're looking at a high level. Go ahead, next slide. Okay, so as I mentioned, we want the GUI to be as familiar as possible. So we've modeled it after existing EEG viewers. And ultimately, as I mentioned, we want to slide into existing workflows as smoothly as possible and attempt not to disrupt any current abilities that users have with their EEG viewers. So everything from Y limits to X limits to control your voltage and time. You can change the channel order, your data, everything like that. So yeah, ultimately just trying to minimize the disruption to existing workflows. Next slide. As I mentioned, on top of minimizing the disruption, we also have these new information to provide with users. So on the time series review tab here, users are able to see when a certain CSD detection event occurred according to the algorithm. And you have these checkboxes available to you, and you can either check or uncheck the boxes to add a little marker into when the event occurred on the time series. And so for each of these data sessions here, these detections will populate with each event, each detection for the given recording session. And then over here, a little bit different than the traditional EEG viewer layout. Our CSD event tab is more focused on looking at individual detection events. And so within the event, you can see the average event velocity. And you can also play a video of the power envelope data in the interval just before and after a detection event was occurred to kind of gain more insights into the spatial temporal space and kind of see what's happening rather than just getting a single timestamp into when the event occurred. Go ahead, next slide. Okay, as I mentioned, kind of going into the transparent pipeline aspect of the GUI, this is borrowed from Alireza's, a slide from Alireza's portion of the talk, and it kind of shows the data as it goes through all the steps of the processing pipeline. So over here, we have raw and DC filtered data. So DC filtered is just our raw data with the near DC frequency component filtered out. So we have these two options, and then we have our delta band, power envelope, and our rectified cross-correlated signal. And these all correspond, if you hit the data type, this is what you see, and all these correspond with various steps along the processing pipeline. And so as I mentioned, I really like this because you can kind of go right down this list and watch the data process in real time. And it just really adds a lot of transparency. Next slide. Okay, now we'll kind of jump into a little bit more into what is meant by offline versus online. Next slide. Okay, so primarily the online and offline GUIs are pretty similar when you look at the data review tab, but the biggest difference and what we'll focus on is the live data stream tab here. So this is in the online GUI. You have this additional tab, which essentially replicates what you would see when watching an amplifier displaying raw data. And so this front end is also connected to a series of data queues or queues and data storage and processing blocks. And so essentially, as this data flows through the GUI, it sits in those queues, and as a critical amount of data is collected, those queues then send the data through the processing blocks when appropriate. And this kind of allows us to start developing code we need to simulate data flows and other things of that nature to prepare for integrating with an amplifier and kind of connecting to that real-time processing that we will eventually need for a clinical setting. Yeah. Awesome. And now we'll kind of jump back to the offline GUI and we'll go over some of the features in a little more depth. So as I mentioned, you can go through the various patient data, select which data you're going to view, also the type of data it is, along with voltage controls, time range controls, your channel order controls, and also a map to display where your channels on the subplot are appearing or where they correspond to in space. So for this example, we're only looking at or we're only focused on the right hemisphere, which is why that's circled. But you can go ahead and change the channel order. And right here, we're looking at the right transverse order. So you can kind of see a really nice spatial display of the order of your channels here. So that you can gain more insight into what's happening with the signals across space by sort of organizing these into more relevant orders. Additionally, you can add some user comments. And so right up here, you can go ahead and just add a comment as well as a time stamp, and it will create a little checkbox here, which are analogous to the detection checkbox, except they appear blue just to mark that they're a different type of marker. Yeah. Then we jump into our CSD event tab and some of the features of that. So one of the features, additionally, you can select a patient ID over here and your data session. And so when you select the data session, it will populate with the summary for that data session. So it can tell you how many events occurred over the length of time of the recording event. And so this is helpful for gathering frequency information for a given recording session, And then you can also see the average event velocity for the selected event. And then, as I mentioned, you can play videos of the power envelope, and that gives users some really nice insights into the pattern of the signal, where it starts, where it goes, and kind of what it looks like, which is an extra added dimension of information we can give to our end users. Awesome. And now just kind of some next steps for our software development efforts. We plan to publish our Python version of WaveFront soon. There's just a couple licensing things that we need to get in order for there. And once we have that all in order, then we can get that out and published. We plan to validate our GUI with some expanded cohorts. This will greatly help with the generalizability and the scalability, just making sure that what we have now scales appropriately when we add cohorts and things of that nature. And it'll also add to the generalizability, as the data assumptions will be slightly different for the various cohorts, and that will just help make it more generalizable for everyone in the future. We plan to integrate some additional information from the CSD-STGAT algorithm, such as the width of suppression for a given detection event. We can add that to the CSD event tab and just provide more information to the end users for a richer experience for them. Next we plan to gather and incorporate some user feedback just to ensure that the layout and functionality is what people want. Then we'll start to move towards software hardware integration. As I kind of alluded to in the online version, we want to start getting our data directly from amplifiers and kind of flowing that all through the pipeline as appropriate. And then finally, we will start working toward the FDA clearance, as we do want to get in clinics very soon, or as soon as possible. Obviously, we'll need FDA clearance for that to happen, so we'll begin working on the pathway for that. And yeah, with that, I'll hand it back over to Alireza, and then we'll go ahead and do a demo.
Thank you so much, John, for the amazing overview of the software development efforts. So here in this slide, I just want to thank all the amazing collaborators who contributed heavily to this work and all the results that we presented today. And also here is the list of grants that supported this work. This work couldn't be done with the amazing contribution of all the undergrad, also master's students who contributed to the CSD-STGAT. I want to give them special credit for that efforts, and we would love to see how does that technique, more advanced technique, perform on the real data set that we collected from our collaborators. Just want to say that we have these two school of thoughts in mind. One is focusing on fully transparent, explainable kind of technique, WaveFront, where the intermediate steps are designed based on the physics of the problem, and also another parallel efforts of like more advanced end-to-end deep learning techniques for better performance, but less explainable, of course, but kind of like at some point merging these efforts together. So yeah, with that, I'm not sure, John, do you want to show us a demo of your amazing WaveFront softwares? If yes, I will stop sharing.
Yeah, no problem. Okay, you guys able to see my screen? Okay, awesome. So yeah, okay, here we are. This is the WaveFront GUI, as I was mentioning earlier. And so up here is kind of where we control our patient data. And so, as I mentioned, this is sort of just a dummy cohort right here. Yeah, let me get these all. And so for right now, we'll just stick with sample patient A, but as you have more cohorts or more patients for your cohort, this is where you would select that. And then if you select sample patient A, it's going to populate with the 3 recording sessions. And so we can go ahead and click through the recording sessions. And as you change that, as I mentioned, this list of CSD detections will also change. And so, for example, we have no CSDs for this event or for that session. And if you have a session that has no events, it will update accordingly. And so additionally, as I mentioned, you can control the data type, your X limits, Y limits, everything like that. And like I was mentioning, you can kind of watch the data flow through the algorithm. So you just sort of click right down and you can see how everything is processed. For me personally, I really like looking at the power envelope signal. For me, that kind of gives the most clarity. But I do like that users can choose which data type they're looking at because it's all personal preference. So yeah. Then additionally, you can change the channel order. As I was saying, that kind of helps give some clarity into looking at where your events occurred and what's going on with them. So for example, if we select this first event, you can kind of see the decline of the power envelope on some of these electrodes that are close together in space. And so, yeah, you can also, as I mentioned, change the channel order if you want. Different events might be easier to see under different orders of channels. Yeah, at a high level, this is sort of the time series review. We can also add comments, as I said. We just add how many seconds after the event it occurred, and it'll just populate with this little user comment right here. And it'll work the same as the CSD detection events. And if you decide you don't want the comments anymore, you can just delete them. Then moving over to the CSD event tab. As I mentioned, you have control over the patient ID over here, as well as the data session. And when you change the data session, it will go ahead and update with the frequency event and or the frequency information. And then you can also go ahead and change the video that you have the ability to play just by clicking through these various event options. And so we'll play a couple. Here's one. You can kind of see the event kind of traveling from P8 to about C4 there. And then we'll take a look at one more over in August 18th. Yeah. And then this is a nice clear one too. You can see it kind of starting from the top and coming down. And so as I mentioned, I really like this tab because it just adds an extra layer of insight into what's going on with the various events, and just kind of provides a nice clean visual to look at. But yeah, that's sort of at a high level the GUI. So yeah, if anyone has any questions, I'm happy to answer them. But I want to thank you guys all for your time and hope you have a great holiday season. Thank you.
Thank you, John, for the nice demo. Yeah, happy to take questions. We have time, I think. Yeah.
Perfect. Yeah, I have some questions for you.
Okay.
The first question, I really liked, John, how you were showing the different parts of the signal processing. And something that came to mind was when I saw that processing pipeline, I thought, wow, that looks really complex. So I was wondering, are these SD events visible in raw EEG or not at all?
Yeah, maybe I can take that question based on my experience of like playing with lots of different patients and hours and days of recording of all the patients. Not at all. ICU data is quite noisy, dirty, even noisier than a normal research-based like EEG recording based on my experience of having worked with both. That's the first question. The other question is that the important and the secret recipe for success in the pre-processing pipeline, which is by the way available open source if you want to take a look, is the careful outlier rejection and the pruning steps that are done based on the different quartiles that we use using Tuckett fence method and also the power envelope extraction, and only then looking at the compressed version of the hours of recording, like for example, every 4 hour or every 24 hour, you may be able to see some correlated patterns with the ground truth in time. So we haven't collected all the spatial detection data yet. We are in the process of that. So stay tuned for the results on that. But of course, for the simulated data, we have shown that we have spatial temporal like consistency around the part that CS is happening. And for some of the actual real patients that I presented the 2 videos for TBI and subarachnoid hemorrhage, we do see those tiny bumps. I can actually maybe project again. They are also happening at the same time and then at the same kind of like space where we have the ground truths for SD, but these are preliminary. So we need more data, better training process, but these are the things that shows up after the pre-processing. Yeah. If that makes sense.
Wow. Yeah, that's incredible to see.
Yeah.
I have one more question and then I'll look to the chat. My question is about clinical applications. So I'm wondering, could the ability to detect CSDs non-invasively lead to earlier interventions? And what kind of treatments might benefit most from this early detection?
Yeah, you're pointing to a very important active, basically research direction in the field, as well as also talking to active conversation with clinicians or collaborators. Since there is no automated SD detection technique like clinically FDA approved, and it's not part of the standard of the care, obviously there is no defined protocol about what doctors should do with this. But based on lots of increasing number of clinical research data, they have shown multiple different techniques are quite effective. And one is, for example, ketamine. Ketamine has been shown very effective as an anesthetic to stop and prevent the propagation of SDs. So if we can have this wavefront as a way of early detection and prediction of the worsening brain damage, then doctors can definitely use the available techniques that have been shown to be effective, at least on the research side. But these are 2 parallel efforts in the field, detection part and also interventional techniques. Other techniques such as transcranial direct stimulation techniques have been shown to be effective in animal models of ST, for example, mice. But it's a work in progress. That's one.
Very cool. Yeah, thanks. Cooper asked if we can go back to the model performance slide where you're comparing the patients with skull and without skull.
Sure. We can do this, cross-validation without generalizability. Then we have the results with generalizability as well. But
Cooper asks, can you elaborate on how incorporating patients with the skull present would enable the model to do better on the specific skull not present subgroup?
That's a great point. I mean, it's counterintuitive at the first sight, and I would say good eyes. It's a good point. Patients without skull, like I said, they have some challenges. They add some challenges to the detection, such as breach rhythm. Because of the imperfection in skull, absence of a skull would mess up with some lower frequency components that we are actually relying on for non-invasive detection. The other answer is the accumulation of air pockets underneath the parts that we are detecting in scalp. That will also reduce the conductivity and also make it more challenges. That's one possible explanation why we get better results for skull present versus skull absent. The other thing is that we have different types and different number of patients for each. If I go back, that may also be some sort of information that's used that might be useful. So we have like 15 skull absent, we have 17 skull present, but for the skull absent, we have different types of injuries. For example, myoclonic hemispheric stroke from Berlin, traumatic brain injury from UC, for the skull presence, we have different cohort of patients, TBI from Mass General Hospital, subarachnoid hemorrhage from Mass General Hospital, and also from Berlin SSH. I would say that may also be a contributing factor. So we only rely on these results at preliminary set of results. We need to have larger cohort of patients across multiple different type of injuries to be able to do perfect comparison. Yeah.
Sure, yeah, that makes sense. In terms of the generalizability of models, it's important to get those large cohorts so that across age, across
sure.
medications and different regions, that all of that generalizes. So you're just planning to get some larger cohorts at some different locations to improve the generalizability of the model?
That's a plan. We are in active conversation with more centers, both within US and outside US, so that we get more data. We should also understand and acknowledge the fact that obtaining these data is very hard. And it's quite challenging. So it's a very unique data set that involves both simultaneous invasive recording and non-invasive recording from different neurological disorders. Each of them have different challenges of obtaining the data. So it's not easy to obtain a large cohort of patients, but people within the field of neurocritical care and COSBIT group, they are actively working on that. And they are sharing the data with us so that we can validate our technique.
I have another question. This is really cool. Oh, sorry. Beyond acute monitoring, do you see applications for WAVEFRONT in long-term monitoring or in conditions where CSDs are suspected but not currently monitored?
Yeah, that's a very good point. Actually, another place that SDs are happening is in migraine aura patients. So aura is a condition where like spreading depolarization may happen after the onset of like the migraine attack or during the onset of migraine attack, and then it can propagate in the visual cortex that shows up as some blurred parts in the vision that propagates slowly, goes away. Or they may happen in the motor cortex, which is called motor aura, that may show up as numbness in limbs or like other sensations in scalp. We have already collected some data with our collaborators in Switzerland, Franz Ruderier from COSBIT Group, and we are already applying the WAVEFRONT. That being said, migraine aura is the hardest SD to be detected non-invasively because it has very small widths of suppression, less than 1 centimeter widths of suppression, and that makes it very hard, especially if you have low density EEG. That's why for the cohort of migraine aura patients, we have an ultra high density EEG cap EGI system around 256 electrodes that we are applying our WAVEFRONT, and we are optimistic that we pick up the patterns, but we don't have the results yet. So stay tuned on that.
We absolutely will. One more question from the chat, and I think we'll finish up. The question is, do you guys envision this eventually going beyond driving clinical management and being a high priority output that diagnoses conditions, or on which clinicians can base their intervention?
Yeah, I would say we started this with the idea of like helping sport players, football players, for example, and we got this funding from Chuck Noll Foundation, Steelers, to help with the concussion monitoring on the sideline, for example, even for soldiers on the sideline to be able to monitor as a quick apply kind of like technique and quick monitoring for early assessments. That was the initial idea. And then also we had this parallel effort started with migraine with and without aura patients. So I would say these are like sort of the eventual goal is to help patients who will not go through invasive surgeries to have access to an automated way of monitoring worsening brain damage, which is like mild TBI or concussion and migraine, where we don't have access to invasive monitoring.
Especially if you're not able to get them into hospital.
Yep, that's right. Also, I would say that's a relevant point that we have this DI effort, diversity, equity, inclusion efforts at Precision Neuroscopic, that we have active efforts on making the EEG more accessible and more applicable to everyone with different hairstyles, and like coarse and curly hair is the main specific part of our hardware development efforts. We've designed several electrodes that will significantly increase the quality of signals on that are collected on the scalp. And that would also be a good addition to our software product to make this diagnostic monitoring product accessible and available to everyone.
Yeah, that's really, really interesting stuff, guys. Thank you both for coming on. It's been a pleasure hearing about your work, and I'm so glad you could be here.
Thank you so much for having us. It was a pleasure to be with you today.
Yeah, thank you so much for having us. It was awesome.
Of course, yeah. And also thank you to everybody for tuning in. If you want to stay up to date with the latest from Moberg Analytics, subscribe to our newsletter, the Neuroscience Monitor, and find us on social media at the links. And thank you guys so much. We'll see you next month.